Today I'll be looking at Chapter 4 of the Engel's Reid Physical Chemistry book. Looking at problems 4, 8, 11, and 15. It's a little short, but it's kind of a short chapter. I think that covers the majority of the information that maybe you use. Number 4. Calculate the delta H of formation standard for NO gas at 975 Kelvin, assuming that the heat capacities of all of the reactants and products are constant over the temperature interval at their values from 298.15 Kelvin. So we're looking at the chemical reaction for this. N2O2 NO gas. However, because it's heat of formation, this is the one time we can use fractional coefficients. So I have to look at the delta H formation. Well, for pure elements at 298, it's going to be 0. Looking up in the back of the book for NO, heat of formation at 298, it is 91.3 kilojoules per mole. Now, another important thing would be calculating your C sub P sub M. It's 29.9. 9.9. N2 gas is 29.1. And O2 gas is 29.4. Now, we want that T at 975 Kelvin. To do this, we have to remember one simple little thing. That delta H at 975 is going to be equal to delta H at 298 plus N C sub P sub M, delta C sub P sub M, dt. When we have to integrate that from 298.15 to, in this case, 975. Now, because these are all constants, it makes it a little bit easier. We're calculating this for 1 mole. This one is just 91.3. But we have to calculate what is our, that's our delta H at 298. Our change in C sub P sub M is going to be equal to products minus reactants all over the coefficient. So 29.4 times 1/2 and 29.1 times 1/2. With that in mind, our C sub P sub M C sub P sub M 29.9 minus 4 is 0.65 joules per mole Kelvin. So integrating this, so the delta H for the integral is going to be 0.65 975 minus 298.15. However, this is going to be units of joules per mole, so times 1 kilojoule, there is 1,000 joules. Between 975 and 298.15 is 676.85. Divide by 0.65, divide by 1,000. Means this effect is essentially 0.43999525. Adding this onto, so our delta H, adding this on, 93.1 plus 0.4, we'll say 44, rounds up to really 93.5 kilojoules. Not a huge change, but it's still a change. Oh, wait, sorry, my bad. 90. Sorry, I dyslexic. It's 91.3. That becomes 91.7. 91.7. Still not a big change from the actual number, but it is a observable change. Looking at number 8. Number 8 is a Hess's law problem. Using the following data at 298.15 Kelvin to complete the problem. So we have 4 equations. We have 1/2 H2 plus 1/2 O2 gives you OH, gas, at delta H for that one of the reaction is 38.95. We have H2 plus 1/2 O2 goes to H2O, gas. That's negative 241.814. We have H2 can be split into 2 H's at a positive 435.994. And O2 can be split into 2 O's at a positive 498.34. And they want us to calculate delta H a reaction for 3 different things. Assuming the gas behaviors, then calculate delta H sub R and delta U sub R for all 3 reactions. So first things first, let's calculate delta H sub R for these guys, since we're given the delta H of these reactions. Now, with that in mind, reaction 1 is we want OH goes to an H and an O. So we want OH splits into an H and an O. So we have O's present in this equation. If H is present in this equation, be OH present in that equation. So I'm going to use a reverse. I'm going to call that equation X. Well, no, I can't use equation alpha, beta, gamma, delta. I'm going to have to use a reverse of equation alpha. So negative alpha. And I'm going to have to use 1/2 delta, or 1/2 gamma, and 1/2 delta to make that work. So I have negative 38.95 And we have adding 435.994 divided by 2, adding 498.34 divided by 2. All that, so you'd have a half O2, a half H2, cancels with a half H2 and a half O2. So 498.34 divided by 2 plus 435.994 divided by 2 plus a negative 38.95 should give you positive 428.217. That's for equation A. Equation B is we want water, steam splits into 2 hydrogens and 1 oxygen. So water is there. So I'm going to use, but since it's a product I need as a reactant, I'm going to split that into 1 equivalent of that, but reverse beta. We're going to have 1 full equivalent of delta, but a half equivalent of one full equivalent of gamma, a half equivalent of delta. So that in mind. So I'd have positive 241.814. We'd have plus 435.994 plus 498.34 divided by 2. Right, 814. So I have positive 926.978 kilojoules. Equation C, last one here. We want water gas splits into H and OH. In this case, we want water gas, we want OH, we want H. So once again, would have a negative beta, but this time would have a positive alpha and a half equivalent of gamma. Because so you'd have 1 half H, adds up to 1 half H, which is 1 whole H, which would cancel out with the 1 whole H there. Would have 1 half O2, cancel out with 1 half O2. Put that in mind. So you'd have 241.814, positive 38.95, and 435.994 divided by 2. 1.814 plus 38.95 plus 5.994 divided by 2. I get 498.761. So all that is how we calculate delta H. Now, how do we calculate U? Well, H is equal to delta U plus PV. Well, once again, using ideal gases, we don't know P, we don't know V, but using ideal gases, we can say PV equals nRT. So our delta U is going to be delta H minus nRT. We're assuming T is 298.15. R is straightforward. So the question is, Rn, what is the change in moles of gas for each one? What is the change in moles of gas? So for equation A, the delta N is going to be, we go from 1 mole of gas to 2 moles of gas. So we're going to get it 2 minus 1, so positive 1. Oh, we're going to have 428.217 minus 1 times 8.314 times 298.15 divided by 1,000. Oh, shoot. So 428.217 minus 814 times. You get, oh, it's dropped. U is 425.735. Now B, what is our delta N? Our delta N for B is, we go from 1 mole of gas to 3 moles of gas. 3 minus 1 is 2. So we're going to take our 926.978 minus 2 times 8.314 times 298.15 or 1,000. So 926.978. So you drop to 922.020. And the last one for C, our delta N, we're going from 1 mole of gas to 2 moles of gas again. So 2 minus 1 is 1. So it's going to be our 498.761 minus 1 times 8.314 times 298.15 over 1,000. So flipping between the two is pretty easy. So I get 496.282. So U and H are relatively close to the same numbers. But that, how you do Hess's law. Problem number 11. At 298 Kelvin, the delta H of reaction is, delta H reaction is 131.28 for the following reaction. C graphite was water gas goes to CO gas and H2. The C sub B sub M is 85.3, or 8.53, sorry. 8.53, 33.58, 29.12, and 28.82 for graphite, water, CO, and H2 respectively. Calculate the delta H reaction at 240 degrees C, with this information. Assume the heat capacities are independent of temperature. So T, we want 240C. So when it says these are independent of temperature, it means we don't have to have a complicated integral equation. We're going to say, we're going to just use the full value. 240 plus 273.15. We're doing this at 513.15. So once again, our delta H at 513 is going to be equal to delta H standard plus the integral of our delta C sub P sub M dt from 298.15 to 513.15. First thing we got to do is we got to calculate our C sub P sub M. So products 28.82 plus 29.12 minus 8.53 and minus 33.58. So this is our delta C sub P sub M. 28.82, 29.12, 33.5 would give us 15.83, because we're essentially figuring out how much energy it takes to heat up the graphite to 240, heat up the water to 240, heat up the CO to 240, essentially cool the CO back down on, well, I said heat up the CO to 240 and heat up the H2 to 240. So we have 131.28 plus 15.83. We got to divide by 1,000 to get this into kilojoules. 513.15 minus 298.15. $513.15 is 215 times 15.83 divided by 1,000. This whole term goes to 3.403. Adding that to the 131.28 becomes 134.68. We've gone up by a couple kilojoules. Not once again, not by a huge amount, but by enough. Last problem here. Problem number 15. Benzoic acid, 1.36 grams. Benzoic acid of C6, well, actually C7, H, what, like 6O2? Because benzoic acid. Benzoic acid, C7H6O2, is reacted with oxygen in a constant volume calorimeter to form water, liquid, and CO2 gas at 298 Kelvin. The mass of water in the inner bath, the mass of water is 1.55 times 10 to the third grams. The temperature of the calorimeter and its contents, the delta T is 2.76 Kelvin. Calculate the calorimeter constant. So C7H6O2 plus O2 goes to CO2 gas, water, liquid. So if this is benzoic acid, I'm assuming it's a solid. It's a gas. I gotta bounce this guy. Say 7, 3, 14, 17, 15. So we can do that. 7 halves. No, wait. 15. Maybe 15 halves. 15 halves, yeah. 15. Okay. Okay, so they want us to calculate what is the heat capacity constant for the calorimeter for this. We need a bunch of different values to do this. But the basic equation is in a constant volume calorimeter, it's a hermetically sealed bubble. So the delta U of the whole system is 0. Because that's true, we can say the delta U of the reaction plus the essentially the heat of the water plus the heat of the heat of the calorimeter will all add up to be 0. The heat of the water is going to be what? The moles C sub P sub M of the water delta T. The heat of the calorimeter would be our C sub P sub M for the calorimeter delta T. And our delta U of the reaction is something we can calculate. So let's first find what is our C sub P sub M of the water. Remember, water being H2O liquid is 75.3. That's one. We need to calculate our delta U of the reaction. But in order to do this, we need the delta H. So let's look at water liquid. So the delta H value of water liquid, so this guy is 0. The delta H of water liquid, since I already have it handy, negative 285.8. The delta H of CO2, it's nearby, is 393.5. And then I have to look up benzoic acid, which is going to be in table not 4.1, but 4.2, which is C7H, which is, oh, we can calculate the heat. Oh, we can probably cheat and say the heat of combustion is negative 3303. 82.9. But let's just double check that. 3303. And so negative 285.8 times 3 plus negative 393.5 times 7 minus 82.9. Well, oh, sorry, not 3303. It's benzoic acid is, I underlined the wrong one. Benzoic acid is 385.2 and would be negative 3227. And that's essentially what I get. I get negative 3,226.7. Okay, so I'll use the delta H of the reaction is negative 3,226.7. So delta U is delta H minus nRT. Well, N, or change in N, we have 15 halves moles of gas on the left and 7. So 15 half is 7.5, and we have 7 moles of gas on the right because the water is a liquid. So our change is negative 0.5 moles. So you're going to add it's a negative minus a negative, add in a positive. So 0.5 times 8.314 thousand. And since we're doing this at essentially 298, our delta U so we have a slight modification of 1.239 grams. So adding that to our negative 3,226.7, our delta U becomes negative 3,225. We'll say 5.5. So that right there is our delta U of reaction in kilojoules per mole. However, we need to find out how many moles. Here's where the 1.36 grams comes in. So delta U for the actual reaction would be our negative 3,225.5 times 1.36 grams divided by what is the molar mass of benzoic acid? It is 122.13. So that would be, all said and done, negative 35.9 kilojoules. Okay, so negative 35.9 kilojoules. So let's figure out what is our heat of water. So we need our mass of water. 5 times 10 to the third grams divided by a molar mass of water, which is about 18. See if it gives us any more accurate number. So might as well cheat and take it. 18.015. And times our heat capacity, 75.3. And finally, our change in temperature, which was a lousy 2.76 Kelvin. However, we also have to divide that by 1,000 to get this into kilojoules. So all that stuff comes down to that term comes down to 17.88. So 17.88 plus a negative 35.9 gives me negative 18.0 plus the C sub P delta T. And all that's equal to 0. All that's equal to 0. Last step, we need to find the C sub P. We add the 18 to the other side. 18.0 equals a C sub P times our 2.76 again. So dividing our 18.0 divided by 2.76 gives the heat capacity for the calorimeter at 6.5 we'll say 6.53 kilojoules per Kelvin. 6.53 kilojoules per Kelvin. So that is how you find the heat capacity constant for the bomb calorimeter. Now, with that in mind, you could then go on to do other problems with that calorimeter knowing the heat capacity. But that's always the first thing that needs to be determined. And that right there is a good example of all the types of problems. Oh, shoot. There's one minor error. That's 1.35 grams there, not 1.36. So that changes my number oh so slightly. That becomes 35.7, which means it becomes 17.8. 17.8 divided by 2.76, 6.45. But okay. Not a big change. Okay, see ya.